This is the EdExcel A-Level Maths Paper 1 from the 2021 series. Question number 1. f of x is equal to ax cubed plus 10x squared minus 3ax minus 4. Given that x minus 1 is a factor of f of x, we have to find the value of the constant a. You must make your method clear. First of all, through the factor theorem, if x minus 1 is a factor of f of x, then f of 1 is equal to 0. What is f of 1? Well, f of 1 is equal to a lots of 1 cubed plus 10 lots of 1 squared minus 3a lots of 1 minus 4. So, a times by 1 is a. 10 times 1 squared is 10. Minus 3 times by 1 times by a is minus 3a. Then we've got the minus 4. And tidying all of this up, we end up with f of 1 equaling 6 minus 2a. Now that we know what f of 1 is, we can set this equal to 0. So, we've got 6 minus 2a equaling 0, and therefore we can conclude a is equal to 3. And knowing that a equals 3, we can therefore conclude f of x is equal to ax cubed, so we have 3x cubed plus 10x squared minus 3ax, so we've got minus 3 times by 3, which is minus 9, and then of course we've got the x, and then we've got the minus 4. f of x is 3x cubed plus 10x squared minus 9x minus 4. Question 2. Given that f of x is equal to x squared minus 4x plus 5, where x is a real number, for part A, we have to express f of x in the form x plus a all squared plus b, where a and b are integers to be found. The form here suggests to us we need to complete the square. Completing the square for part A, we begin with f of x equaling x squared minus 4x plus 5. If we complete the square, halving the coefficient of x, we end up with minus 2. So, we have x minus 2 all squared. We then take away the square of 2, which is 4. We then add 5. And so therefore, we can conclude f of x is equal to x minus 2 all squared plus 1. we can of course, conclude A is equal to -2 and B is equal to 1. Now, for part B, the curve with equation y equals f of x meets the y-axis at the point P and has a minimum turning point at the point Q. We have to write down the coordinates of P and the coordinates of Q. Where the graph meets the y-axis, that's when x is equal to 0. And you can see when x is equal to 0, we have 0 minus 0 plus 5, which is 5. So P has coordinates 0, 5. And for the second part, the coordinates of Q we can find using the form given here. Q has coordinates 2, 1. Question number 3. The sequence U1, U2, U3, etc. is defined by UN plus 1 equals K minus 24 over UN, where U1 is equal to 2 and K is an integer. Given that U1 plus 2 lots of U2 plus U3 equals 0, for part A, we have to show that 3k squared minus 58k plus 240 equals 0. So, for part A, we begin with U1 equaling 2. We have U1, which is equal to 2. To find out what U2 is, U2 is equal to, using the iterative formula, K minus 24 over U1. So, we have U2 equaling K minus 24 over 2. Indeed, you can see U2 is equal to K minus 12. And knowing that U2 is equal to K minus 12, we can now find out what U3 is. U3 is equal to K minus 24 over U2. So we have K minus 24 over U2, which is K minus 12. And so therefore, U3 is equal to K minus 24 over K minus 12. We now know what U1 is, we know what U2 is, we know what U3 is. And we are given that U1 plus 2 lots of U2 plus U3 equals 0. So, with U1 plus 2 lots of U2 plus U3 equaling 0, we have 2 plus 2 lots of k minus 12 plus k minus 24 over k minus 12. Adding these together, we get 0. We now need to simplify all of this. We have 2 plus 2k minus 24 plus k minus 24 over k minus 12 equals 0. Two k plus k is 3k, 2 minus 24, that's minus 22, and then we subtract 24 over k minus 12. Again, this is all equal to 0. Let's now multiply through by k minus 12. We've got k minus 12 lots of 3k minus 22 minus 24 equals 0. Let's expand and simplify. K times by 3k is 3k squared. K lots of negative 22, that's negative 22k. And then we have negative 12 times by 3k, that's negative 36k. So negative 36k minus 22k is minus 58k. And then we have minus 12 times by minus 22, that's plus 264. And then we've got the minus 24. This is all equal to 0. And so if we tidy all of this up, we've got 3k squared minus 58k plus 240 equals 0. And that's exactly what we wanted to show. And now for part B, we have to find the value of k, giving a reason for your answer. Well, for part B, if we factorize this quadratic, we have k minus 6 lots of 3k minus 40 equals 0. And if we attempt to solve, you can see k is either equal to 6 or 40 over 3. Now, we can conclude k equals 6 is the only solution, and that's because k is an integer. And now for part C, we have to find the value of U3. Well, knowing what k is, we can therefore conclude that un plus 1 equals 6 minus 24 over un. And we also know u1 is equal to 2. Now, we found before that u3 is equal to k minus 24 over k minus 12. And with k equaling 6, you can see u3 is equal to 6 minus 24 over 6 minus 12. And if we work this out, what we end up with is 6 plus 4, which is 10. And so therefore, u3 is equal to 10. Question number 4. The curve with equation y equals f of x, where f of x equals x squared plus the natural log of 2x squared minus 4x plus 5, has a single turning point at x equals alpha. For part A, we have to show that alpha is a solution of the equation 2x cubed minus 4x squared plus 7x minus 2 equals 0. For part A, we begin with f of x equaling x squared plus the natural log of 2x squared minus 4x plus 5. Differentiating f dash of x is equal to, well, if we differentiate x squared, we end up with 2x. And if we differentiate the natural log of 2x squared minus 4x plus 5, what belongs on the denominator is 2x squared minus 4x plus 5. And if we differentiate this, we end up with 4x minus 4. Now the reason we had to differentiate is through this statement, single turning point. And we know with a turning point, that would suggest to us f dash of x equals 0. So now what we need to do is set f dash of x equal to 0. And if we do that, we have 2x plus 4x minus 4 over 2x squared minus 4x plus 5 equals 0. If we attempt to simplify all this and write this in the required form, we have 2x lots of 2x squared minus 4x plus 5 plus 4x minus 4. And this is all equal to 0. If we expand and simplify, 2x times by 2x squared, that would be 4x cubed. 2x times by minus 4x, that's minus 8x. 2x times by 5, that's 10x. We add on 4x and then we subtract 4. This is all equal to 0. So, what we end up with, if we collect like terms, is 4x cubed minus 8x squared plus 14x minus 4. This is all equal to 0. And if we divide through by 2, you can see 2x cubed minus 4x squared plus 7x minus 2 equals 0. Now, for part B, the iterative formula xn plus 1 equals a seventh lots of 2 plus 4xn squared minus 2xn cubed is used to find an approximate value for alpha. Starting with x1 equals 0.3, we have to calculate, giving each answer to 4 decimal places, the value of x2 and x4. So, with our iterative formula and x1 equaling 0.3, we can find out what x2 is. x2 is equal to 1/7 lots of 2 plus 4 lots of x1 squared minus 2 lots of x1 cubed. If we type into our calculator 0.3, currently 0.3 is stored into the answer function. We have 1/7 lots of 2 plus 4 lots of answer squared minus 2 lots of answer cubed. What we end up with then is x2 equaling 0.3294, etc. given to 4 decimal places. We've got 0.3294 to 4 decimal places. Now, to find out what x3 is, that's equal to 1/7 lots of 2 plus 4 lots of 0.3294, etc. squared minus 2 lots of 0.3294, etc. cubed. So if we work this out, press the equals button, what you will find is x3 is equal to 0.3375, etc. And what we need to do is find out what x4 is. So x4 is equal to 1/7 lots of 2 plus 4 lots of 0.3375 etc. squared minus 2 lots of 0.3375 etc. cubed. So if I press equals again, we end up with x4 equaling 0.3398 etc., which, given to 4 decimal places, we've got 0.3398 given to 4 decimal places. Now for part C, using a suitable interval and a suitable function that should be stated, we have to show that alpha is 0.341 to 3 decimal places. Well, we have this cubic function currently, and of course 2x cubed minus 4x squared plus 7x minus 2 is equal to 0. So what we can do is let h of x equal what we have on the left hand side, and then we can use the change in sign method to show that alpha is 0.341 to 3 decimal places. For part C, let's define h of x. H of x is equal to 2x cubed minus 4x squared plus 7x minus 2. And of course we are solving h of x equals 0. Now, in terms of the interval we will use, if we pay attention to what we want to show alpha is, we want to show alpha is 0.341 to 3 decimal places. So it makes sense for us to consider a lower bound and an upper bound of the 0.341. What I mean by that is, we will work out h of 0.3405, and we will also work out h of 0.3415. And of course, once we get a change in sign, we can therefore conclude that alpha is equal to 0.341 in between these values here. So let's work out h of 0.3405. With our calculator, we type in 0.3405. This is now stored in the answer function. We've got 2 lots of this cubed minus 4 lots of this squared plus 7 lots of this minus 2. What we end up with is a value of minus 0.00130, etc. And if we work out what h of 0.3415 is, we've got 2 lots of this cubed minus 4 lots of this squared plus 7 lots of this minus 2. what we end up with over here is 0.00366, etc. And so therefore, there is a change of sign and f of x is continuous in the required interval. And so therefore, alpha is equal to 0.341 given to 3 decimal places. And of course, what we mean by the required interval alpha will be in between 0.3405 and 0.3415. So alpha is equal to 0.341 given to 3 decimal places. Question number 5. A company made a profit of £20,000 in its first year of trading, year 1. A model for future trading predicts that the yearly profit will increase by 8% each year, so that the yearly profits will form a geometric sequence. According to the model, for part A, we have to show that the profit for year 3 will be 23,328. For part A, if we have a geometric sequence, of course, with a geometric sequence, un is equal to a, the first term, multiplied by r to the power of n minus 1. We are finding the profit in year 3. In other words, we are finding u3. And this is equal to 20,000, A is 20,000, multiplied by 1.08, of course, the 1.08 is due to the increase by 8% each year. And then we will raise this to the power of 3 minus 1. So therefore, if we work out what u3 is, 20,000 multiplied by 1.08 to the power of 3 minus 1, we get 23,328. And so, therefore, we can conclude that the profit in year 3 is 23,328. For part B, we have to find the first year when the yearly profit will exceed 65,000. Well, if we use our geometric sequence for part B, we've got 20,000 multiplied by 1.08 to the power of n minus 1 using this. And we are looking for the year in which the yearly profit will exceed 65,000. So this result is greater than 65,000. So if we find out what n is, well, we've got 1.08 to the power of n minus 1 being greater than we have here 65,000 divided by 20,000, which is 13 over 4, or 3.25. And now if we take the natural logarithm of both sides, we've got n minus 1 multiplied by the natural log of 1.08 being greater than the natural log of 3.25. So n minus 1 is greater than the natural log of 3.25 over the natural log of 1.08. So n minus 1 is greater than the natural log of 3.25 over the natural log of 1.08, which is 15.31, etc. N, of course, is greater than 16.31, etc. So therefore, we would have year 17 in which the profit exceeds £65,000. And now for part C. We have to find the total profit for the first 20 years of trading, giving an answer to the nearest £1,000. If we take a look in the formula book, here is the result for the sum of a geometric series. And so therefore S20 is equal to 20,000 multiplied by 1 minus 1.08 to the power of 20 over 1 minus 1.08. And if we work out the value of this, 20,000 multiplied by 1 minus 1.08 to the power of 20 divided by 1 minus 1.08. It turns out we get 915,239.286, and so therefore we have £915,000, of course, given to the nearest 1,000. So we have £915,000 to the nearest £1,000. Question number 6. Figure 1 shows a sketch of a triangle ABC. We're given that AB is equal to minus 3i minus 4j minus 5k. We are also given BC equals I plus j plus 4k. We have to find the vector AC. The vector AC that's equal to the sum of AB and BC. We know the vector AB, that's minus 3i minus 4j minus 5k. We know the vector BC is I plus j plus 4k, and therefore the vector AC, we've got minus 3i plus I, which is minus 2i, minus 4j plus j is minus 3j, and minus 5k plus 4k, that's minus k. Here is the vector AC. For part B, we have to show that the cosine of ABC is equal to 9/10. Before we do that, let's add on this vector AC. AC is minus 2i minus 3j minus k. If we redraw that triangle, what we will do is redraw the triangle, also adding on the magnitudes of the lengths. Here is the triangle as required. Now, what we will do is find out the magnitudes of AB, BC, and AC. If we find out the magnitude of AB, that's equal to the square root of minus 3 squared plus minus 4 squared plus minus 5 squared. It turns out here we get here 5√2 for AB. So we will add on to our diagram 5√2. Let's find out what BC is in terms of its magnitude. 1 squared plus 1 squared plus 4 squared is 3√2. We have 3√2 here. AC, we have minus 2 squared plus minus 3 squared plus minus 1 squared. We get √14. So we will add on to our diagram √14. If we now use the cosine rule, the required angle is the angle ABC. That's this angle here. So, using the cosine rule, we've got AC squared, which is equal to AB squared plus BC squared minus 2 lots of AB times by BC times by the cosine of the angle ABC. So let's substitute everything in. We have AC squared, so that's √14 squared, which is 14. This is equal to AB all squared. 5√2 all squared is 50. BC all squared, well, 3√2 all squared is 18. Then we will take away 2 lots of AB, which is 5 root 2 times BC, which is 3 root 2 times by the cosine of ABC. And so with simple rearranging, the cosine of ABC, that's equal to 50 plus 18 minus 14 divided by 2 times by 5 root 2 times by 3 root 2. And so therefore, if we work all of this out, 50 plus 18 minus 14 over 2 times by 5 root 2 times by 3 root 2, indeed we get 9 over 10. So the cosine of ABC is equal to 9 over 10. Question number 7. The circle C has equation x squared plus y squared minus 10x plus 4y plus 11 equals 0. We have to find the coordinates of the centre of C and the exact radius of C, giving your answer as a simplified surd. First of all, what we need to do is complete the square. This allows us to find the radius and the centre. If we complete the square focusing on the x's only, half of the coefficient of x is minus 5. So we have x minus 5 all squared. We then take away the square of 5 in terms of the y's. Half of the coefficient of y is 2. So we have y plus 2 all squared. We then take away the square of 2. And then we have plus 11. And this is equal to 0. So we have x minus 5 all squared plus y plus 2 all squared equals, well, here we would have 5 squared plus 2 squared, take away 11, which is 18. And so therefore, you can see the centre would have coordinates 5 minus 2, and the radius is equal to the square root of 18, which is 3 root 2. Now for part B, the line L has equation y equals 3x plus k, where k is a constant. Given that L is a tangent to C, we have to find the possible values of k, giving it answers as simplified surds. Let's sketch the problem. You can see here we've got two possible scenarios. We've got our straight line y equals 3x plus k touching the circumference once, and the two possibilities arise, of course, would have different values of k, and that's all relating to the y-intercept. So what we will do is, to begin with, we will substitute into C L. we will replace the y with 3x plus k. So if we substitute in equation 2 into equation 1, we have x squared plus 3x plus k all squared minus 10x, and then here we have plus 4y. So we've got 4 lots of 3x plus k, and then we add on 11, the result of which is 0. Let's expand and simplify. X squared plus 9x squared plus 6kx plus k squared minus 10x plus 12x plus 4k plus 11 equals 0. If we rewrite this in the simplest form, x squared plus 9x squared, that will be 10x squared. In terms of the x's, we have 6k minus 10 plus 4, rather 6k minus 10 plus 2 plus 12. So here we would have 6k plus 2 x's, and then we add on, in terms of the numbers, k squared plus 4k plus 11, and all of this is equal to 0. And of course, because L is a tangent to C, the discriminant is equal to 0. So we have b squared minus 4 times by, rather here we've got b squared minus 4 ac equals 0. And if we use the discriminant, we can then form a quadratic to find the possible values of k. So, using the discriminant, we have b squared, so that's 6k plus 2 all squared, minus 4 lots of a, lots of c, and all of this is equal to 0. We now need to expand and simplify. 6k plus 2 all squared, well, we have 36k squared plus 24k plus 4 minus 40k squared minus, well, here we've got 4 times 10 times by 4, so that's minus 160. Okay, and then here we've got 4 times 11 times 10, which is minus 440. And all of this is equal to 0. So, if we take everything over to one side and simplify, we have 4k squared plus 136k plus 436 equals 0. And if we find out what k is, Of course, here we can just use our calculator. 4k squared plus 136k plus 436, we get minus 17 plus minus 6 root 5. This is the value of k we require. Question number 8. A scientist is studying the growth of two different populations of bacteria. The number of bacteria, N, in the first population is modelled by the equation N equals AE to the power of KT, where T is greater or equal to 0. A and K are positive constants, and T is the time in hours from the start of the study. Given that there were 1000 bacteria in this population at the start of the study, and it took exactly 5 hours from the start of the study for this population to double, you have to find for part A a complete equation for the model. Well, at the start of the study, there were 1000 bacteria. So, when T equals 0, N is equal to 1000. So we have 1000 equals e to the power of 0 multiplied by a. So we've got 1000 equals ae to the power of 0. Of course, a is equal to 1000. And knowing that a is equal to 1000, we can therefore conclude n so far is equal to 1000 e to the power of kt. We are also told it took exactly 5 hours from the start of the study for this population to double. So when t equals 5, we've got 5 hours, n then is equal to 2000. Of course, double the 1000 is 2000. So we've got 2000 equals a e to the power of 5k. Now we already know what a is. So we've got 2000 equals 1000 e to the power of 5k. And if we simplify, 2 equals e to the power of 5k. 5k is equal to the natural log of 2. And therefore k is equal to 1/5 times by the natural log of 2. And so therefore n is equal to 1000 e to the power of 1/5 times by the natural log of 2 multiplied by t. For part B, hence find the rate of increase in the number of bacteria in this population exactly 8 hours from the start of the study. Give your answer to 2 significant figures. For part B, because part B concerns rates, we would have to differentiate. So if we differentiate, dn over dt, this is equal to, well, we've got the 1/5 times by the natural log of 2 multiplied by 1000 e to the power of 1/5 times by the natural log of 2 multiplied by t. And if we attempt to tidy this up, a fifth times by 1000 is 200. So we've got 200 times by the natural log of 2 multiplied by e to the power of 1/5 times the natural log of 2 times t. Now when t is equal to 8, of course we have 8 hours, dn over dt is equal to 200 times by the natural log of 2 multiplied by e to the power of 1/5 times by the natural log of 2 times by 8. So if we work all of this out, 200 times by the natural log of 2 times by e to the power of 1/5 times the natural log of 2 multiplied by 8, we get 420.24. And so therefore, we would have 420 to 3 significant figures. And now for part C, the number of bacteria M in the second population is modelled by the equation M equals 500e to the power of 1.4 kt, where t is greater or equal than 0. And k has the value that we found in part A, and t is the time in hours from the start of the study. Given that t hours after the start of the study, the number of bacteria in the two different populations was the same, we have to find the value of t. Well, using our value of k and setting this equal to this, for part C, we have 500 times by e to the power of 1.4 times by k, and we know what k is. That's 1/5 times by the natural log of 2, and then we're going to multiply this by t, and this is equal to 1000 e to the power of 1/5 times by the natural log of 2 multiplied by t. We need to find out what t is. So here, if we divide through by 500, we have e to the power of, now we've got 1.4 divided by 5, which is 0.28. So we have e to the power of 0.28 times by the natural log of 2 times by t. This is equal to 2e to the power of 0.2, which is the same as 1/5, times by the natural log of 2 multiplied by t. So what we need to do is find out what t is. If we divide these by each other, we have e to the power of 0.28 times the natural log of 2 times by t divided by e to the power of 0.2 times by the natural log of 2 times by t. This is all equal to 2. Now, when we have the same base and dividing, we can subtract the powers. So, we have e to the power of 0.08 times by the natural log of 2 times by t equals 2. And if we now take the natural log of both sides, we have 0.08 times by the natural log of 2 times t equals natural log of 2. So what we need to do is find out what t is. T is equal to natural log of 2 over 0.08 times by the natural log of 2. So therefore, t is equal to 1 over 0.08, which is 12.5. So what we end up with is 12.5 hours. Question number 9. f of x is equal to 50x squared plus 38x plus 9 over 5x plus 2 all squared lots of 1 minus 2x, where x doesn't equal minus 2/5 and x doesn't equal 1/2. And given that f of x can be expressed in the form a over 5x plus 2 plus b over 5x plus 2 all squared plus c over 1 minus 2x, where a, b and c are constants, for part A we have to find the value of b and the value of c and show that a is equal to 0. So for part A, what we need to do to begin with is multiply through by 5x plus 2 all squared lots of 1 minus 2x. This will get rid of any fractions. And if we do that, we've got 50x squared plus 38x plus 9 being equivalent to a lots of 5x plus 2 lots of 1 minus 2x plus b lots of 1 minus 2x plus c lots of 5x plus 2 all squared. And what we need to do is find the values of a, b and c. Well, we can eliminate the bracket here and here by letting x equal 1/2. And if we let x equal 1/2 on the left hand side, we've got 50 lots of 1/2 squared plus 38 lots of 1/2 plus 9. This bracket disappears, so the a terms disappear, the b terms disappear. We are left with, on the right hand side, c lots of 5 times by 1/2 plus 2 all squared. If we substitute in a half on the left hand side, we get 50 lots of this squared plus 38 lots of this plus 9. We get 81 over 2 on the left hand side. And on the right hand side, we get 5 times by a half plus 2 all squared, we get 81 over 4 on the right hand side, multiplied by c. And so therefore, we can conclude c is equal to 2. Now, if we let x equal minus 2 over 5, on the left hand side, we've got 50 lots of minus 2 over 5 squared, plus 38 lots of minus 2/5 plus 9 on the left hand side, and on the right hand side the a term disappears, the c term disappears. We are left with b lots of 1 minus 2 lots of minus 2/5. So we've got 50 lots of this squared plus 38 lots of this plus 9. We get 9 over 5 equals, well, here we've got 1 minus 2 times by minus 2/5. So here we get 9 over 5b on the right hand side. Of course, b is equal to 1. Now, if we let x equal 0, say, on the left hand side we've got 9, and on the right hand side we've got a lots of 2 lots of 1 plus b lots of 1 plus c lots of 2 squared. 9 equals 2a plus b plus 4c. We know that c is equal to 2 and b equals 1. So we've got 9 equals 2a plus 1 plus 4 times by 2. 9 equals 2a plus 9. A is equal to 0. And knowing the values of a, b and c, we can therefore conclude 5x squared plus 38x plus 9 over 5x plus 2 all squared lots of 1 minus 2x is equivalent to 1 over 5x plus 2 all squared plus 2 over 1 minus 2x. Now, for the first part of part B, we have to use binomial expansions to show that in ascending powers of x, f of x is equal to p plus qx plus r x squared, etc., where p, q and r are simplified fractions to be found. Well, in the formula book, we need to use this version of the binomial expansion. So, doing so, let's split the terms separately and work them out. We have the 1 over 5x plus 2 squared being the same as 5x plus 2 to the power of minus 2. This being the same as, if I take out, well, let's rewrite this as 2 plus 5x, of course, due to commutativity, we can do that. We've got 2 plus 5x to the power of minus 2. And if I take out a 2, I've got 1 plus 5 over 2x. And what I'm doing is raising this to the power of minus 2. So we have 2 to the power of minus 2, lots of 1 plus 5 over 2x to the minus 2, which is what we need to work out. So using our expansion, we've got 2 to the power of minus 2. Now if we pay attention to the question, we're going up to x squared. So what we have is 1 plus negative 2 multiplied by 5 over 2x over 1 factorial plus negative 2 lots of negative 3 lots of 5 over 2x squared over 2 factorial. We could continue on. And if we do continue on, well, 2 to the power of minus 2, that's 1 over 4. So we've got 1 over 4 multiplied by 1, and then here we've got 5 over 2 times minus 2, which is minus 5. X, of course we're dividing that by 1 factorial, and then here we've got minus 2 times minus 3 times by 5 over 2 x squared over 2 factorial. It turns out here we get 75 over 4 x squared. And then we could continue on. And if I expand and simplify this even further, we've got 1 over 4 minus 5x over 4 plus 75 x squared over 16. We also have higher order terms. Let's now focus on the 2 over 1 minus 2x. 2 over 1 minus 2x, we've got 2 lots of 1 minus 2x to the power of minus 1. So if we expand this out using the binomial, we've got 2 lots of well, here we've got 1 plus minus 1 times minus 2x over 1 factorial. Then we've got minus 1 times minus 2 times minus 2x squared over 2 factorial. And then we could continue. So we've got 2 lots of 1 plus 2x. Here we have 4x squared times by minus 1. So that will be 4x squared So if we expand all of this out, we end up with 2 plus 4x plus 8x squared. And now the entire expansion is the sum of those two. So therefore, f of x is equal to 1 over 4 minus 5x over 4 plus 75 x squared over 16 plus 2 plus 4x plus 8x squared, and then we continue with higher order terms. So now if we tidy all of this up, we have a quarter plus 2, which is 9 over 4. In terms of the x's, we've got minus 5 over 4 plus 4, so that's 11 over 4. And in terms of the x squared, 75 over 16 plus 8 is 203 over 16. And then we've got other terms as well with it. And now we have to find out the range of values for which the expansion is valid. Well, if we take a look at what we had here, we've got, once we've factorized out everything, we've got this being, rather here we've got the mod of x being less than 2 over 5. And then here, this one is valid for x being, the mod of x being less than 1/2. So we want the one which is smaller, so therefore this is valid for the mod of x being less than 2 over 5. Question number 10. For part A, given that 1 plus cos 2 theta plus sin 2 theta doesn't equal 0, we have to prove that 1 minus cos 2 theta plus sin 2 theta over 1 plus cos 2 theta plus sin 2 theta is equivalent to tan theta. Well, if we focus on the right hand side, so far we've got tan theta, and we know that tan theta is the same as sin theta over cos theta. And how does that help us? Well, let's take a look at what we have on the left hand side. We've got 1 minus cos 2 theta plus sin 2 theta over 1 plus cos 2 theta plus sin 2 theta. Now somehow I want a sin theta over a cos theta. I want this result to simplify to sin theta over cos theta. I want the top to involve something involving sines and the bottom to involving something involving cosines. Now, if we use a known identity for cos 2 theta is the same as 1 minus 2 sine squared theta. Now here you'd notice we've got 1 minus 1, which is 0. That's useful to know. And then the sine 2 theta will leave as 2 sine theta cos theta. And on the bottom, we've got 1 plus cos 2 theta. Now let's make sure the bottom has something involving cosines. It might make our life a lot easier. We've got 2 cos squared theta minus 1, and then of course sine 2 theta is the same as 2 sine theta cos theta, and of course the 1 and the minus 1 cancel out. So let's see what we can tidy up so far. Well, we've got minus and a minus, so that's plus, and then we've got 2 sine squared theta, and then we will add on 2 sine theta cos theta, and on the bottom the 1 minus 1 cancels, and then here we've got 2 cos squared theta plus 2 sine theta cos theta. Now the 2's cancel everywhere on the top and bottom, so we are left with, well, let's just show that the 2's cancel on the top and bottom, and if on the top I factorise out a sine theta from both terms, we've got sine theta lots of sine theta plus cos theta, and on the bottom we've got cos theta if I factorise that out, and then here we've got cos theta plus sine theta. Now due to commutativity, this and this cancel out, leaving us with sine theta over cos theta, which is tan theta. And that's exactly what we wanted to show. Now for part B, hence solve for x being in between 0 and 180, 1 minus cos 4x plus sine 4x over 1 plus cos 4x plus sine 4x equals 3 sine 2x. Hopefully what you can recognise is 2 theta rather, is equal to 4x, so theta equals 2x. So theta equals 2x. Now, if we use the result from part A, this result over here will equal tan 2x. So, using part A, we've got tan 2x, which is equal to 3 sine 2x. And now we need to tidy all of this up. Well, tan 2x is the same as sine 2x over cos. 2x. This is equal to 3 sine 2x. And if I multiply through by cos 2x, we end up with sine 2x equals 3 sine 2x cos 2x. And if we take everything over to one side, we've got sine 2x minus 3 sine 2x cos 2x equals 0. And if I factorize out a sine 2x, sine 2x lots of 1 minus 3 cos 2x equals 0. So either sine 2x equals 0, or we've got cos 2x, which is equal to 1/3. Now, we are only solving in between 0 and 180 if we take a look at this domain. So, first thing we will do is change the domain. So we've got 0 being less than 2x being less than 360. So if sine 2x equals 0, let's solve this. 2x is equal to, well, let's make sure we're in degrees. Inverse sine of 0 is 0. So the next solution is at 180, take away 0, which is just 180. And then that's the only solution we have in the required domain, because 2x cannot equal 360. So here we would have x equals 90. And if we now focus on the cos 2x equals 1/3, 2x, that's equal to, well, the inverse cosine of 1/3, that's 70.52, etc. Store this into A. And then if I do 360 minus this, I get 289.47, etc. Store this into B. So therefore x is equal to, well, if I divide this by 2, I get 144.7 degrees to one decimal place. And if I do A divided by 2, I get 35.3 degrees to one decimal place. So x is equal to 35.3 degrees, 90 degrees, 144.7 degrees, all given to one decimal place where appropriate. Question number 11. Figure 2 shows a sketch of part of the curve with the equation y equals the natural log of x all squared, where x is greater than 0. The finite region R, shown shaded in figure 2, is bounded by the curve, the line with equation x equals to the x-axis, and the line with equation x equals 4. The table below shows corresponding values of x and y, with the values of y given to 4 decimal places. For part A, we have to use the trapezium rule with all of the values of y in the table to obtain an estimate for the area of R, giving an answer to 3 significant figures. Before we do anything else, let's label these y values y0, y1, y2, y3, y4. Now, in the formula book, under the numerical methods section, we have the formula for the trapezium rule. That's shown highlighted. Now, h over here is equal to 0.5. To go from the 2 to the 2.5, we add on 0.5. Same thing here. We add on 0.5. Same thing here. And same thing here. So therefore, you can see h is equal to 0.5. And so if we use the trapezium rule for part A, the area is approximately equal to the integral between 2 and 4 of the natural log of x squared. We've got 1/2 times by h, which is 0.5, multiplied by we've got y0, 0.4805, plus y4, 1.9218, plus two lots of the y values in between, 0.8396, 1.2069, and 1.5694. So if we work all of this out, let's use our calculator. We've got 1/2 times 0.5 times by 0.4805 plus 1.9218 plus two lots of the values in between, 0.8396, 1.2069, 1.5694. It turns out we get 2.408525 or 2.41 given to three significant figures. So therefore the area of R is equal to 2.41 to three significant figures. Of course, here we have units squared. Now, for part B, we have to use algebraic integration to find the exact area of R, giving your answer in the form y equals a lots of the natural log of 2 squared plus b lots of the natural log of 2 plus c, where a, b and c are integers to be found. Well, clearly what we need to do here is find out the result of this integral here. So let's do that. Part B. We begin by finding out the integral between 2 and 4 of the natural log of x squared. So if we do that, we need to use the product rule, rather the integration by parts formula, which, if we go to the formula book, is over here for us. So we've got u, u dash, v dash, and v, which we need to find. We have here the natural log of x all squared being the same as the natural log of x multiplied by the natural log of x dx. So if we work all of this out, u is equal to the natural log of x. So u dash is equal to 1 over x. V dash is equal to natural log of x. And v, well, to do that, what we need to do is find out the integral of the natural log of x, which is the same as 1 times by natural log of x dx. Now, in this case, u is equal to natural log of x, u dash is equal to 1 over x, v dash is equal to 1, v is therefore equal to x. So, the integral of the natural log of x with respect to x is equal to uv, so that's x times by the natural log of x minus the integral of v u dash. So we've got the integral of 1 with respect to x. So we end up with x times by the natural log of x minus x. So that means v over here is equal to x times natural log of x minus x. Let's just reorganize all of this. So having reorganized all of this, we can now work out what this is all equal to. Well, here, what we can conclude is the integral from 2 to 4 of natural log of x all squared. We've got u times by v, so we have natural log of x multiplied by x times by natural log of x minus, well, let's just take out the limits for a moment, minus the integral of v u dash. So here we've got v u dash, we've got 1 over x multiplied by x times by natural log of x minus x. So, taking out an x as a common factor, we've got x times by natural log of x multiplied by natural log of x minus 1 minus the integral of natural log of x minus 1 dx. Now, the integral of natural log of x we've just worked out. So, we've got x times by natural log of x times by natural log of x minus 1 minus. Now, natural log of x, that is equal to x times by natural log of x minus x. And then here, the integral of minus 1 is minus x. And then we've got the plus c. So let's expand and simplify. We've got x times by natural log. Let's just tidy all of this up properly. We've got x times by natural log of x all squared minus x times by natural log of x. We subtract another x times by natural log of x. And then we've got the minus 2x, so that will be positive 2x. And then we've got plus c. So what we end up with over here then is x times by the natural log of x all squared minus 2x times by the natural log of x plus 2x plus c. So what we now need to do is work all of this out using our limits. So the integral from 2 to 4 of natural log of x all squared with respect to x is equal to x times by natural log of x all squared minus 2x times by natural log of x plus 2x in between 2 and 4. Now, if we substitute in for our upper limit, we've got 4 lots of the natural log of 4 squared, and here we have minus 2 times by 4 times by natural log of 4, and here we've got 2 times by 4. That's what we get for the upper limit. And for the lower limit, substituting in 2, we've got 2 lots of natural log of 2 all squared minus 2 times by 2 times by natural log of 2 plus 2 times by 2. So we need to tidy up all of this even further. And if you remember to what the question said, we want our answer to involve natural log of 2's only. Now we know that 2 squared is equal to 4. So we've got 4 lots of natural log of 2 squared negative 16 times by natural log of 2 squared, and then we have eight. That's for the upper limit, and for the lower limit, 2 lots of natural log of 2 squared minus 4 times natural log of 2 plus 4. So if we work all of this out, we have here 4 times by 2 times by natural log of 2 all squared minus 32 natural log of 2 plus 8, and then we've got 2 times by natural log of 2 squared minus 4 times by natural log of 2 plus 4. So if we tidy all of this up, well, 2 squared, that's 4. Rather here, there was a slight mistake. 2 times by 4 is 8, and over here we would have 16. Now 4 times by 2 squared, that's 16. So we've got 16 lots of natural log of 2 all squared. So that comes from the fact that we've got 2 squared, which is 4, timesing that by 4, we get 16. And we've got minus natural log of, we've got minus 16 lots of the natural log of 2 plus 8 minus 2 times by natural log of 2 squared minus 4 times by natural log of 2. Well, we've got minus and a minus, so that's a plus, and then we've got the minus 4. So if we tidy all of this up, you can see we end up with 14 times by natural log of 2 all squared minus 12 times by natural log of 2 plus 4. So this is the final result. Question number 12. We have figure 3 over here, and figure 3 is a graph of the trajectory of a golf ball after the ball has been hit until it first hits the ground. The vertical height h, meters, of the ball above the ground has been plotted against the horizontal distance travelled, x meters, measured from where the ball was hit. The ball is modelled as a particle travelling in a vertical plane above horizontal ground, and given that the ball is hit from a point on the top of a platform of vertical height 3 meters above the ground, reaches its maximum vertical height after travelling a horizontal distance of 90 meters, and is at a vertical height of 27 meters above the ground after travelling a horizontal distance of 120 meters, and given also that h is modelled as a quadratic function in x, for part A we have to find h in terms of x. Well, if h is a quadratic in x, what we can say then for part A is h equals ax squared plus bx plus c. And what we need to do is find out what a, b and c are. Now if we take a look at the h-axis, when x is 0, h is 3. So when x is 0, h is 3. So we've got 3 equals 0 plus 0 plus c. C is equal to 3. And so knowing that c is equal to 3, we'll start off by saying h equals ax squared plus bx plus 3. Now, we also know that it is at a vertical height of 27 meters above the ground after travelling a horizontal distance of 120. So, when x is equal to 120, h is equal to 27. So, we've got 27 equals a lots of 120 squared plus b lots of 120 plus 3. 24 equals 14,400 a plus 120 b. So that's what we've got so far, and we know that it reaches a maximum height when x is equal to 90. Now if we have a maximum height, that suggests to us we need to differentiate. So if we differentiate dh over dx, that's equal to 2ax plus b. And we know that when x is 90, we've got a maximum height. So dh over dx is 0. 2a times by 90 plus b equals 0, which means 180a plus b equals 0. If I call this 1 and if I call this 2, we can solve equation 1 and 2 simultaneously. So we've got 14400, 120, 24, 180, 1 and 0. You can see a is equal to minus 1 over 300 and b is equal to 3 over 5. And knowing the values of a and b and c, we can therefore conclude h is equal to minus x squared over 300 plus 3x over 5 plus 3. We have found a quadratic. Now for the first part of part B, we now have to find the maximum vertical height of the ball above the ground. Well, we know that the maximum height occurs when x is equal to 90. So, when x is equal to 90, h is equal to minus 90 squared over 300 plus 3 lots of 90 over 5 plus 3. So if we work out what h is, we've got minus 1 over 300 times 90 squared plus 3 over 5 times 90 plus 3, we get 30 meters. And now for the next part, we have to find the horizontal distance travelled by the ball from when it was hit to when it first hits the ground, giving an answer to the nearest meter. So of course, when it hits the ground, that's when h is equal to 0. So we've got 0 equals minus x squared over 300 plus 3x over 5 plus 3. So if we find out what x is, we're expecting to get two values. We've got minus 1 over 300 plus 3 over 5 plus 3. We get x equals 184.86. And we also get minus 4.868. And so therefore, we have 185 meters given to three significant figures. This is horizontally. Now for part C, the possible effects of wind or air resistance are two limitations of the model. Give one other limitation of this model. Of course, the ground is unlikely to be horizontal. That's one possible limitation. Question number 13. A curve C has parametric equations x equals t squared plus 5 over t squared plus 1 and y equals 4t over t squared plus 1 where t is a real number. We have to show that all points on C satisfy x minus 3 all squared plus y squared equals 4. Well, if we begin with our parametric equations, we have x equals t squared plus 5 over t squared plus 1. We also have y equals 4t over t squared plus 1. So we have x minus 3. So we have x minus 3 all squared plus y squared. And if we substitute in as necessary, we've got x, which is t squared plus 5 over t squared plus 1. And then we've got the minus 3 all squared plus y squared. So we will square 4t over t squared plus 1. Now we need to tidy all of this up. Well, one way in which we can tidy all of this up is to rewrite this so we've got common denominators. So we've got t squared plus 5 minus 3 lots of t squared plus 1 over t squared plus 1 all squared plus 4t over t squared plus 1 all squared. T squared minus 3t squared, that will be negative 2t squared, and then we've got the 5 minus the 3, so that's 2. So we've got 2 minus 2t squared over t squared plus 1 all squared. And then we will add to this 4t over t squared plus 1 all squared. So we've got 2 minus 2t all squared plus 4t all squared all over t squared plus 1 all squared. And if we expand and simplify, what we end up with is 4 minus 8t. Just realised that was a mistake. It should be 2 minus 2t squared squared. So we've got 4 minus 8t squared plus 4t squared plus 16t squared divided by t squared plus 1 all squared. So we've got 4t squared plus 8t plus 4, rather 4t to the power of 4 rather, plus 8t squared plus 4 divided by t squared plus 1 all squared. So we've got 4 lots of t squared, rather t to the 4, plus 2t squared plus 1 over t squared plus 1 all squared. And this is the same as on the top, t squared plus 1 all squared. We will divide this by t squared plus 1 all squared, which is indeed 4. And that's exactly what we wanted to show. Question number 14. We're given that y equals x minus 4 over 2 plus square root x, where x is greater than 0, and we have to show that dy over dx is equal to 1 over a square root x, where x is greater than 0 and a is a constant to be found. Well, here we are differentiating a fraction, and you may recall, to differentiate a fraction we would need to use the quotient rule. So we know already y is equal to x minus 4 over 2 plus square root x, which I'm going to write as x to the power of 1/2. So when we come to use the quotient rule, u is equal to x minus 4, u dash is equal to 1, v is equal to 2 plus x to the power of 1/2, and v dash is 1/2 x to the power of minus 1/2. So if we use the quotient rule to differentiate, dy over dx is equal to v times by u dash minus u times by v dash over v squared. So we will divide this by 2 plus x to the 1/2 squared. So if we tidy this up as much as we can, we've got 2 plus square root x minus, well, here we need to be a bit more careful. We've got x times by 1/2, and then we're going to multiply that, we're going to multiply the x by the x to the minus 1/2, so add the powers. Here we get x to the 1/2, and then we've got minus and a minus, which give a plus, so we will add on 4 x to the minus 1/2, and then we will divide this by 2 plus x to the 1/2 squared. So what we now need to do is tidy this up as much as possible. So we've got 2 plus square root x minus 1/2 square root x plus 4 over square root x, and then we will divide this by 2 plus square root x squared. So what we will do course here we've got a 2 because 4 times a half is 2. So now if we tidy this up even further, each term in the numerator and the denominator we will multiply by root x. So we've got 2 times square root x plus square root x times square root x minus 1/2 times by square root x times by square root x plus 2. That's what we have on the top. And on the bottom, we've got square root x, lots of 2 plus square root x squared. So, we've got 2 square root x. And then here we've got x minus a half x, which is minus a half. So that's going to be plus 1/2 x, because I've got root x, which is just x. And then I'm adding on 2. And on the bottom, we've got root x, lots of 2 plus square root x squared. So now, if we attempt to tidy this up, what we would have to do now is multiply through by 2 on the top and bottom. So we're going to have 4 times square root x plus x plus 4. And on the bottom, we would have 2 root x times by 2 plus root x squared. Now, through commutativity, we've got x plus 4 times by square root x plus 4 on the top, and on the bottom, we've got 2 root x times by 2 plus square root x squared. Now, let's expand along the bottom. Along the bottom, if we square, we would have 4 plus 4 root x plus x, and along the top we have x plus 4 square root x plus 4. This and this cancel, leaving us with 1/2 square root x. Of course, we can conclude here a is equal to 2. Question number 15 for the first part. We have to use proof by exhaustion to show that for n belonging to a set of natural numbers where n is less than or equal to 4, n plus 1 all cubed is greater than 3 to the power of n. Well, when n is 1, n plus 1, we would have 1 plus 1 cubed, which is 8. And then on the other side, we have 3 to the power of 1, which is 3. we see here 8 is greater than 3, so the statement is true in this case. When n is 2, we've got 2 plus 1 cubed, which is 27. On the other side, we've got 3 to the power of 2, which is 9. We see that 27 is greater than 9. The statement is true when n is equal to 2. When n is 3, we've got 3 plus 1 cubed, which is 64. On the other side, we've got 3 to the power of 3, which is 27. We see that 64 is greater than 27, so the statement is true in this case. And finally, when n is 4, we've got 4 plus 1 cubed, which is 125. And then we've got 3 to the power of 4, which is 81. 125 is greater than 81. The statement is true in this case. So what can we conclude? Well, we can conclude then, if n is less than or equal to 4 and n is a natural number, then n plus 1 all cubed is greater than 3 to the power of n. Question number 15 for the second part. We're given that m cubed plus 5 is odd, and what we have to do is use proof by contradiction to show that, using algebra, m is even. Well, if we use proof by contradiction, we begin by stating the opposite. If here the statement is m is even, then we begin by letting m be odd. And if m is odd, that implies that m can be written in the form 2p plus 1. So m cubed plus 5 is the same as 2p plus 1 to the power of 3 plus 5. So if we expand this out, we've got, if we use the binomial, we've got 1 lots of 2p cubed times 1 to the 0 plus 3 lots of 2p squared lots of 1 to the 1 plus 3 lots of 2p to the 1 lots of 1 squared plus 1 lots of 2p to the 0 lots of 1 cubed, and then we will add on to this 5. So we've got 8p cubed, 4 times by 3 is 12, and then we've got the p squared with it. 2 times by 3 is 6. We've got 1, and then plus the 5. We've got 8p cubed plus 12p squared plus 6p plus 6. And if we take out a 2, then what we've got here is 2 lots of 4p cubed plus 6p squared plus 3p plus 3, and this result is even. So this result here is even. And now what we said over here, if m is odd, then m cubed plus 5 is even. That's a contradiction. So Because we've got some sort of a contradiction, what we can therefore conclude then, well, if you think about it, we've just shown that m cubed plus 5 is even, despite being told it's odd. So, contradiction. If m cubed plus 5 is odd, then m must be even. So this is the concluding step.